All right. Good morning. I'm very happy to have the opportunity to talk to you a little bit about the Low Density Materials Program. I've been at AFOSR now for about 2.5 years, and this program is about the same age, although it does have heritage in the polymer matrix composites program that Dr. Charles Lee used to run. So most of the projects I'll present to you today are about 2 years old or less. But there are a couple that really exciting work that I have Dr. Lee to thank for that I'll also highlight that have been in the program for a little longer than that. Okay, I think every person that gets here has this problem. Okay, you hit that one? Mm-hmm. Okay, so here, this program is really looking at advanced materials to enable substantial reductions in system weight with enhancements in performance and function. And I'll talk more about what that really means, in particular enhancing performance and function as we go along. Whenever you think about low density, decreasing density, you think about specific properties in materials. And so I like to see that this portfolio is really focused on increasing the specific performance of aerospace platforms. There are 3 sub-areas that I've divided the portfolio into: structural lightweighting, multifunctionality, and hybrid materials. And tell you in real simple terms what each of those mean to me as we go along, but for the sake of explaining these arrows, I'd like to just point out now that the area of structural lightweighting, there was a large component of that in the polymer matrix composites program, and so we've kind of maintained a steady level of investment in that area. The area of multifunctionality, multifunctional materials, is a growth area for the portfolio, and that growth has largely come in the form of a Miri that we just launched this year. We have 2 new Miri teams on this area, so I'll tell you more details about that as well. And then lastly, an area that should become a continued area of growth for us, and this is the area of hybrid materials, where we're actually looking at designing materials from the bottom up. So, so we'll go into more detail on those as I brief some of the projects within the portfolio. One other point I'd like to make here is that over the past 2.5 years, I've really made an increased and very deliberate effort to forge more interdisciplinary teams to really address kind of broad-based problems within this particular area. And so I'll point some of those out, some of the teams that we've tried to forge. Sometimes they self-aggregate, and then sometimes I kind of do a little of encouragement and pushing people with complementary expertise to form teams. Okay, before I go into the projects and the highlights, I'd like to talk a little bit about and give you my commercial on why low density materials. RSA, Dr. Fuller's directorate, has a slogan that goes something like, if it has structure and rises above the ground, then RSA is steward of the fundamental science in that area. And so I'd like to coin that and say that if it has structure and rises above the ground, that material density is important. And in a soon-to-be released National Academy of Sciences study on lightweighting, the team there has really done a good job in conveying and making a strong case for the importance of lightweighting and material density, and conveyed its impacts on the mission. This study was focused not just for the Air Force, it was for all 3 services, and so they talked about lightweighting and density and that type of thing in Army and Navy as well. But it talks about and shows the impacts in things like payload capacity, the range of your mission costs, things like attributes in terms of the performance of your mission, agility, survivability, and even environmental impact. So I would refer you to that document, which should be released at any point, which makes a really strong case for a program like the Low Density Materials Program. So here is my favorite triangle, if you've seen me brief before. And this triangle really kind of serves as an outline for my talk. It has the 3 sub-areas of the program, and the first sub-area is structural lightweighting. Structural lightweighting, simply put, for me, what that means is taking the weight out. It's taking the weight out of traditional materials and components that make up the materials used in aerospace airframe platforms. And we can do this in a couple of ways. One way is by making the materials and the properties better, improving those properties, making them stronger, more resilient, such that we can use less of a given material to meet a given specific need. You can also do that by doing things like enhancing or incorporating porosity, looking at porous structures and nanoscale porosity into structures. And so we have about 1/4 of the portfolio that is focused in this area, looking at a variety of concepts for structural lightweighting. And I'll highlight a few of those here today. This first group and project that I'd like to highlight is a really good example of that encouraged teaming that I mentioned at the outset. As a matter of fact, before funding this program, one of the reviewers commented that this was a dream team for doing this type of research. The team is Joycelyn Harrison at University of Nebraska at Lincoln, who's more in the nano manufacturing, nanomechanics, some polymer composites expertise. Dr. Stephen Chang, who is in the area of polymer physics and characterization, and then Dr. Frank Harris, who's world-renowned polymer chemist, who in particular for high-performance polymers like polyimic chemistry. And so when you bring this kind of diversity together on a team, you end up with some pretty unique approaches to innovation and discovery. And so what this team is doing is trying to make nanofiber reinforced structures. Now we know that the state of the art in terms of reinforcing structures are either the reinforcements either a glass fiber or a carbon fiber. And here the group is looking at reinforcing with polymer nanofibers. And to do that, you really need materials that have the right combination of properties and processability in order to get nanofibers that are going to be strong enough and have the right suite of properties and processability to use them for reinforcing structures. So what this team has done, the synthetic expertise here, is looked at polyimic chemistry and making new polymers, novel material systems here, looking at new compositions of matter in terms of diamines and dianhydrides, and incorporating the right functionalities into these monomers to get you the properties that you ultimately need to be able to process these materials and to get the ultimate properties you like to see. So they're doing things like incorporating bulky, steric hindering type groups, incorporating kink linkages into the backbone chemistry, in this case in the diamine, doing copolymerizations to reduce the periodicity in the structure. And all these are really targeting getting a nice soluble imide that is imidizable in one step, in this case chemically imidizable in a single step, and then being able to redissolve that so that you can process it and make a nanofiber. And then you want that ultimate fiber to have the structural rigidity and toughness, and of course thermal stability to be useful in a structure. And so this team has been working on synthesizing several of these types of new chemistries, and then they pass those off to Joycelyn at University of Nebraska. And he's done a really nice job in terms of the nanofabrication and fabricating nanofibers from those new polymers. And in this example, what he's doing, the process, I should step back and say, is electrospinning. And so electrospinning is where you spin a fiber from in the presence of an electric field. So typically puts voltages on the order of 10 to 20 kilovolts and spin these polymer nanofibers. And what he's seen is that at a threshold of about 400 nanometers in terms of fiber diameter, you see a really nice increase in the tensile strength of these nanofibers. And to give you a point of reference, Kevlar, polyaramid Kevlar, has a tensile strength of about 3.5 to 4 gigapascal. These have tensile strength of almost 9 gigapascals, so there's more than double the strength of something like a Kevlar fiber by making these fibers really thin and nanoscale diameters. In addition to this increasing trend in strength with diameter, you've seen that as you go lower and lower in the fiber diameter, you also have a dramatic increase in the toughness. And so yours tells me that these are the strongest, toughest nanofibers ever made. And what's also very interesting about them is that with this increase in strength, you usually see a fall off in the failure strain. But in this case, the failure strain actually increases. It's about 20% greater than you would expect to see, strain of about 47%. So these are really new compositions of matter, new processing to enable nanofiber fabrication. We've always wanted to get to smaller diameter fibers because you know that your probability of defects in fibers goes down as you go to smaller diameter, and this processing enables that. And so we're excited to see where this goes as they continue to work on synthesizing and improving this processing and incorporating these into laminate structures. This next team is working on a really tough problem that has trying to resolve a tough problem that has really evaded the community for the past 20 years since the inception of the nano area. This is an area that I love to talk about because it's a really fundamental problem. It's, how do you translate the really good nanoscale properties that we see in entities like nanotubes? How do you translate those great nanoscale properties to macroscale structures? It hasn't been done. The structures that you see that incorporate nanotubes and nanostructured carbon type conforms in them, they're being used for other things. They're being used because they have great electrical conductivity, or they have EMI shielding capability, but they're not being used because they have good load-bearing structural capability. So why is that? We've been at this now for about 20 years, and we really haven't cracked that nut. And so I think one of the fundamental issues is how do you get good load transfer, good coupling between the nanotubes and with each other, and also coupling the load between the nanotube and the matrix that you have when you're making a composite. And so this team of Ben Wang and Richard Liane, who leads a group of a couple of researchers at Florida State University, Ben, I should mention, it's at Georgia Tech, they're looking at trying to resolve some of the issues associated with this challenge. Their approach is twofold. They're looking first at mechanical consolidation issues, and then secondly at chemical consolidation issues to try to understand this. If you look at the materials that have been made with nanotubes incorporated, nanocomposites, what you'll see that the primary failure mechanism is nanotube pullout. If you examine these under SEM, you see that that's the failure mechanism that is most commonly encountered. And so that tells you that there's a coupling issue going on, that you can't really couple that load across, that you're not coupling that load into the tubes. And so what they're doing in terms of trying to improve mechanical consolidation is taking something like these CNT bundles that you readily get from many of the processing to make them, to make these carbon nanotubes, and looking at how do you get these aligned. These are here in the solid state, kind of brute force alignment of these carbon nanotubes. And then probably even more importantly, how do you get these fully condensed and consolidated such that those tubes start to to flatten out and have really close contact with one another, increasing the contact area of the tubes, the stiffness of the tubes, and the friction between these tubes. All that helps to couple the load. And so they're working these aspects of it. The work is experimental, but it also includes theoretical modeling to try to optimize how you process, do this mechanical consolidation. And then the work also will advance. They're not really in this phase of the work. Will advance to look at how you do the chemical consolidation. You get these nice consolidated mats or assemblages, if you will, of nanotubes. How can you actually cure those, either coupling to matrix resin or coupling tubes with other tubes? And there's been some research done, this is not from one of my PIs, but some research done that shows you can do irradiation-induced coupling or cross-linking between actual nanotube segments. And so this project is looking at those types of approaches for translating those great properties at the nanoscale to macro scale. This next project is a project that, it's a durab. You don't really highlight a lot of durabs very often, but I really wanted to highlight this durab because I think it's a really nice, effort in terms of training tomorrow's workforce and doing really good research. The PI is Dr. David Vesey. David did a summer faculty fellow at RW in the Munitions Directorate with Dr. Jennifer Jordan, and has ongoing research and collaboration with the group down at Eglin. And he's also a part of a HBCU MI proposal that's funded by the AFOSR on nanoparticle reinforced resins for processing to make high temperature, low density composites and energetic materials. So it's a program with a strong link to Air Force interest, and enables this professor and others at these two universities to have a state-of-the-art cutting-edge analysis capability for training and doing good fundamental research. And so the demographic that these two universities reach has a large, highly diverse demographic. And so I think this is an excellent example of work that will have an impact, a significant impact on training tomorrow's workforce for the Air Force and the DoD. So those three projects that I wanted to highlight in the first sub-area. The second is a multifunctionality. And so simply put, what multifunctionality means to me is designing the materials to do more, okay? It's being able to couple load-bearing capability with other useful functions. And that's where we'll go back to being able to really enhance system performance if we have the incorporation of other useful properties that you can get out of these materials in addition to the load-bearing capability. So first project in this area is on slightly different slide than I was expecting, but multifunctionality with, again, with nanotubes. And in this case, this is a drastically different approach than the work that I mentioned of Ben Wang. And this is the approach where he's looking at liquid phase processing of carbon nanotubes. Dr. Matteo Pasquale at Rice University started this work about 2.5, almost 3 years ago. This was work funded originally in the Polymer Matrix Composites program, and I should thank you publicly, Charles, for this because it's been a great research project that's gotten lots of interest, lots of tech transfer, and I'll tell you a little bit about that. And also working with Matteo has just been delightful. What he has done is come up with a way to dissolve carbon nanotubes into a chlorosulfonic acid. So you can get these nanotubes dispersed, and here a couple of years ago, in collaboration with Technion University in Israel, he was able to get a cryo-TEM where you can see that nanotubes are randomly kind of in solution or dispersed in a chlorosulfonic acid solution. And if you look at these under polarized light, you see what looks like liquid crystalline domains, birefringent liquid crystalline domains, similar to like the polyaramid type materials. And so this indicates that these materials might be spinnable and actually made into fibers, and that's what he has done. He's worked to spin these, and these are really the first carbon nanotube fibers that have been made. You see, these are not NanoFibers like the work of in the first project. These are micron size fibers. He's done this work. This work has, as I mentioned, captured a lot of interest, and one company, Teijin Aramids, has been working with him for the past year and a half to really scale up the production or scale up the fabrication. I won't say production because they're not at those quantities yet of carbon nanotube fiber, and measure the properties. And so here's an example of the properties and why this kind of really fits into our multifunctionality load-bearing plus. In the case here, the plus is electrical conductivity. The red dots here represent the carbon nanotube fiber that was synthesized at Rice University. And you can see, if you compare that to the metals, typical metals here, the conductivity of it is pretty good. It's approaching that of silver. However, the strength is much higher. And so you can look at that as a strong conductor, I mean a strong, mechanically strong conducting fiber. If you look at it compared to other typical fibers like polyacrylonitrile fibers and pitch fibers, the conductivity is much higher than these fibers. And there are a lot of applications where you'd like to be able to have this conductivity in a fiber, in a strong, structurally strong fiber. And so in addition to really good electrical conductivity, just last week I got a string of excited emails, a lot of buzz, because the folks at RX at Wright-Patterson have begun to do measurements of the thermal conductivity of these materials, and the thermal conductivity numbers are really, really high. So they were very excited about the early measurements of also thermal conductivity in these structural fibers. And this picture here is a picture where they have it's hard to see, they call it invisible, but this LED is being held up and wired by one of these carbon nanotube fibers. Okay, better move quickly. This work is really kind of similar to the approach of Matteo Pasquale at Rice. It's led by Dr. Micah Green at Texas Tech University, and he is a YIP award winner in the program recently. And what, again, he's trying to do is look at graphene. And again, the issue with many of these nanostructured materials is that you have to be able to get them dispersed in a medium if you really want to use them for structural type applications. And so he's looking at these stabilizers, polymer stabilizers, PVP and pyrene derivatives, and looking at how you can use those to stabilize the graphene such that you can get them dissolved in a solution. And so he's been able to make very nice stable solutions of them. And if you can get that good physisorption of the stabilizers with the graphene, that should lead to good interfacial load transfer that we want to see with these types of materials. So moving along a little more quickly, I'd like to go back to another really favorite subject of mine, and that's boron nitride nanotubes. I keep talking about this. I didn't talk about it last year, but I want to come back to it because there has been some progress in this area, and I also want to pound the point because I'm trying to get a couple of other program managers really excited about this area. I think we need to do more to stimulate this because there are lots of applications that are, in particular for extreme environment type applications, that I think boron nitride nanotubes might be a part of the solution space for. And so Ali's on board with me. I think John Lugansland's on board. And so we're gonna continue to massage that and hopefully come up with a plan. But the reason I'm excited is because of the great properties here. If you compare boron nitride nanotubes to carbon nanotubes, they have comparable mechanical properties. They're semiconducting, and so they're insulating, which is a good fact. But you can also band gap engineer these things to make them conductive if you need to. They have a net polarizability, so they're intrinsically piezoelectric. Boron, we know, particular boron 10 has a strong neutron scattering cross-section, so they're useful for neutron shielding type issues. And then also, these materials have a much higher thermal oxidative stability than carbon. And so, you get up to much higher temperatures, and so this will enable, open up that temperature space for some of the needs in Air Force systems. And so again, here's work that where I've tried to forge a new team to work in this area. Dr. Chanhong K is one of my YIP awardees, and when Changyang has developed a really exceptional capability in his lab for looking at the nanomechanics of nanostructured materials. And there was a capability, and then there's that know-how and finesse for being able to do these extremely delicate measurements like single tube nanomechanics, where you can actually pull out a single nanotube and measure its properties. And so, if you look in the literature, the data can be all over the place depending on who does the measurements. And Dr. K has done a really good job and puts out really good data in this regard. So when he first talked to me about ideas for YIP, he was really mostly focused on carbon nanotubes, and it hit me like, wow, this capability is great. We really need to begin to get some of these measurements in boron nitride nanotubes because they don't exist in a lot of cases. And so, so I hooked him up with folks at NASA and the National Institute of Aerospace who have been leading in synthesizing some boron nitride nanotubes, and also with Dr. Alex Zettel at UC Berkeley. And Alex is the first, is credited as being the first to ever make a boron nitride nanotube. And so now Changhong is connected with that group, and they have done a really good job in the past year and a half. This is one example of the types of measurements they've done, but they've been quite prolific. I think he and Dr. Cho Park at National Institute of Aerospace are about on their 4th or 5th journal publication in this area, because there's just so much exciting discovery going on. But in this case, he's painstakingly separated out single wall, double wall, and triple wall nanotubes, both carbon and boron nitride, and done single tube measurements of the elastic modulus of each of these. And so the carbon is in blue and the boron is in red. And what you see is that the boron nitride nanotubes for each of these different types of tubes have on average a 40 to 60% lower effective modulus than carbon nanotubes. And this is really kind of the first actual measurement of these types of properties. And they have very interesting implications because I mentioned band gap engineering for boron nitride. The band gap decreases as you deform these, and so you can more readily deform these than something like a carbon nanotube. And that also has implications for mechanical reinforcement because, as I mentioned, you want to get that deformation to get good coupling between the tubes and when you're looking at mechanically consolidating these. So these are very interesting results. Also, Dr. Park and Dr. Alex Zettel from Berkeley that I mentioned earlier are working together on this team, and they're looking at doing some of the first piezoelectric and electrostrictive measurements in these materials. And so I mentioned before that these have a net polarizability, and so if you put if you strain these, you see the polarization along the tube or normal to the tube, depending on if you strain it in torsion or tension or compression. And Dr. Park has used what he likes to call his Oreo cookie configuration to actually measure the electroactive properties of this, and sandwiching boron nitride film in between carbon nanotube electrodes. And he's looked at the electrorestrictive strain of these materials, and also here the linear relationship, which is the D33, the piezoelectric coefficient of these materials. And there's much more of this characterization to come, but it shows the potential for, in this case, load-bearing plus actuation. Also, I won't harp on this, but I mentioned before the neutron shielding capability of the boron materials, and so here they've done some very initial work using a neutron source in residence at NASA, and looked at the shielding effectiveness, mu here, of different materials, low-density polyethylene. This is hexagonal boron nitride particles and boron nitride nanotube particles. And because of differences in not having enough material volume, they didn't measure. This is 30% boron nitride particles, and this is only 5% boron nitride nanotube. And neither of these are at saturation. But what they found is that because of the good distribution, your ability to really get good coverage and distribution of the boron particles at the nanoscale by using something like a boron nitride nanotube, that you have a much greater shielding efficiency with a lower weight or mass of boron nitride. And we, of course, know that boron is used commonly in makeups for UV shielding, and so they've done just some beginning experiments to look at UV shielding capability. So here again, the area is load-bearing plus, and the plus is radiation shielding in this particular case. The next area I'd like to move through quickly is talking a little bit about nanostructured carbon. And so if you like carbon, you should be really excited. You've had your heyday in the past 20 years, because starting in the mid-'80s, these new forms of nanostructured carbon have really taken off. And so we have a zero-dimensional fullerene type buckyball configurations, and then Ijima came along with one-dimensional carbon nanotube type structures, and then just in the past couple of years we've seen Nobel Prize winners in the development of two-dimensional graphene type structures. These guys, Richard Smalley and Sir Harry Kroto, and this is Robert Curl, got a Nobel Prize for this work as well. And so we can only hope that maybe there'll be a Nobel Prize here. And this is an area that we're funding on the Miri. It's looking at the possibility of actually making three-dimensional nanostructured carbon type materials. And so this is a kind of a pillared truss network where you have carbon nanotubes integrated with graphene. And we expect a really nice combination of properties. Here we have, this is the topic of Miri that we just had the kickoff for in January of this year. There are 2 Miri teams that are funded here, so there's a pretty large investment that the DoD is making to look at if we can possibly fabricate some of these three-dimensional nanostructured carbon, or not just carbon in this case. Some of the configurations include other entities as well, so, but three-dimensional nanostructures. So here we expect them to have a widespread potential application, everything from electronic type to thermal management, structural, because of their large surface area, things like energy storage and conversion. Thermal management, because you can imagine, as Dr. Joan Fuller mentioned yesterday during her presentation, if you have a photon that you could direct it to travel throughout this truss network, what that might do in terms of the thermal transport in materials like this. And so we're excited. I won't go through the details here of some of the approaches that are being planned, but just to introduce the teams, they're just getting started. The first team is led by Professor Jayan at Rice University, and it has players, Ray Bogman included, that Leslie mentioned earlier, from Texas, University of Texas at Dallas, Delaware, and Penn State are the other team players. And then the other team is being led by Dr. Liming Dai from Case Western University, and he has players from Georgia Tech, Kent State, Purdue, and University of North Texas. So last, I keep saying that I think I need to flip my presentation. I always start at the base and go up to the apex, and then by the time I get to the apex to talk about hybrid materials, I'm out of steam and out of time. So I need to switch next year and start at the apex. But this is a really exciting area, hybrid materials. And what I mean by that, simply put, is designing and building materials from the bottom up. So doing atom by atom type development of materials. Dr. Fuller mentioned earlier in the week that that myself and Dr. Ali Sayer are both involved in the Materials Genome Initiative. And this is the area of the portfolio that is most closely related to the Materials Genome Initiative. So we're going to be working more and integrating into that. So the idea here is really is kind of a paradigm shift is required. Currently what we do is we design a structure based on the limitations and the properties of the material. And what we really want to start being able to do is to design the material based on the structural requirements. And so that's just the fundamental, step change in terms of how we need to think about materials. And what will enable that is if we really can understand how to do real smart materials design. I borrowed this slide from one of my PIs at the lab, Dr. Tim Breitzman. I liked it because it really shows the multidisciplinary span of the materials modeling hierarchy. Here in my portfolio, we really start at the atomistic level. We're going to leave the electronics, that level of physics to our colleagues in the physics organization, Dr. Weinstock and Tatiana. You all are welcome to maintain that ground, but we're going to start here at the atomistic level, and funding work that looks at relating what's happening at individual molecules and how that impacts microscale properties. And then Dr. Stargill's portfolio then takes it from the micro level and looks at what microscale phenomena and how that impacts macroscopic properties. And so here's a hole, though, that we really need to begin to fill in terms of how do these molecular entities impact microscale behavior. And so here's an example of a project. This is one of the lab tasks that we fund at at RX in Wright-Patterson, and he's looking at Tim and Rajiv Berry, also Jim Muller at Miami University. They're looking at connecting atomistic and microscale behaviors. And so they've designed in computational space here this a unit cell of in this case, an epoxy resin, and actually looked at the stress-strain behavior and to determine when the polymer network begins to break down, and correlated that with the number of actual bond breaks within the structure. And they've taken this correlation further to actually map out these bond breaks, this chain scission, bond scission, to tell where within that unit cell did those bonds break. And this level, it took me a while to really have a great appreciation for this, but it will take this level of understanding how the atoms respond to environment, stress, strain, temperature, chemical attack, and other things to really be able to design and know in a predictive way that the material can withstand whatever the requirements of the structure are. And so this is, I see I have 1 minute left. I'm gonna skip this for now and go. David talked a lot about the origami initiative that he, Fariba, Doug Smith, and I are engaged with at NSF. And I was told I have to bring this up because we wanted to mention that we had a nice origami workshop in Korea this past summer, and the team at in our AOTA office were very helpful in coordinating that, Ken Castor and Tom Ernst. So we wanted to mention that our Asian team has been very supportive, even to the extent that Tom has worn an origami tie today. So, and he's standing up in the back to show you that he has his origami crane on. So Joan's shaking her head like, no, she didn't. So, but anyway, so David told you about this initiative, and so I won't belabor it now, but I'd like to kind of close with the 6 seconds I have to mention that we're interfacing with all aspects of the research community. I will point out in particular my involvement with the Reliance 21 board, where all of the services in DITRA and DARPA and others are highly involved. So I serve as the materials and processing point of contact for AFOSR there. And also, I see we have in the audience some of our colleagues that we work closely with at NRO that on nanostructured materials, we're linking and understanding very closely what each other's fund in these areas, as well as our colleagues at NASA who are doing lightweight structures. So in closing, I wanted to acknowledge and show the faces of all the other PIs that are also in the program. And I found that in the past 2.5 years that I've been here, the thing that I really enjoy most, probably as much, if not more, than the great, exciting science that we get to work with and be stewards of, it's working with all these great people. And so with that, I'd like to end and be happy to answer any questions if I have time.